Hi, my name is Marie Lindqvist and this presentation is about logistic regression. Regression models are used in statistics when we want to model the relation between two or more variables. We have one response, also called outcome or dependent variable, and one or more independent variables, also called covariates. So how do you know which regression model to choose? It is the structure of the response that decides which regression model we will use. The linear regression model is used when the response is quantitative and not too skewed. The residuals from this analysis are supposed to be normally distributed. The logistic regression model is used when the response is binary, which means that it can only have two values. For example, a patient is sick or healthy. Cox regression is used when we study time, especially time to a certain event. For example, time to death or time to get a new job. And Poisson regression is used when the response is counts. For example, we want to model what affects the number of customers coming to a shop during 1 hour. There are also many other regression models, but those are the most common. This presentation is about logistic regression and what is the background to this model. If we have a binary response and try to fit a linear regression model, we will have some problems. Firstly, the residuals will not be normally distributed because the response can only take on two values. And second, if we try to predict new values from this model, they can be larger than 1 or less than 0, and we don't want that. And the logistic regression model solves those two problems. To describe the model, we first compare the linear and the logistic models. In linear regression, we model the linear relation between a quantitative response and a covariate. As an example, we model the relation between blood pressure and age. In logistic regression, in the other way, we model the linear relation between the odds for a certain event. In this example, it's the odds for a stroke. And we look at the relation between odds for a stroke and the covariate, in this case age. And here, the vertical axis shows the natural logarithm for the odds for this event. The logistic regression model, also sometimes called the logit model, can be written in this way. The natural logarithm of p divided by 1 minus p equals alpha plus beta x plus the error term. And in this equation, p is the probability that the event y will occur, and p divided by 1 minus p, this is the odds for the event y. So the odds mathematically is written by p divided by 1 minus p. And then the natural logarithm of p divided by 1 minus p is the log odds. And this term is also called the logit. And if we in this equation want to estimate the probability for the event, we can do that by using this formula, and this is calculated from the first equation. This picture shows another comparison between the linear and the logistic regression model. The blue dots are the observations, and the response here is binary. Each observation has a value for the covariate x and a value for the response y. And the value for y can here be only 0 or 1. The green line shows the result if we try to fit a linear regression model to this data. It will not be a line that is very close to any of the points. In the logistic regression, we instead model the probability for the response. And the pink line here shows the shape for the logistic regression model. And the response here will be the probability for the event. We will come back to this picture later when we calculate the probability for a certain event. So how do we then interpret the parameters in a logistic regression model? The model is written like this. And if we relate to the linear regression, the slope coefficient beta can be interpreted as the change in the log odds when x or the covariate increases 1 unit. And this is not very practically and not very useful interpretation. So instead we can use the odds ratio. And it can be shown mathematically that the exponential of beta is the odds ratio for the event associated with a unit increase in x, a unit increase in the covariate. We illustrate this with an example. We have a sample of septic patients and their Apache 2 score is measured. The Apache 2 score is a measure of severity of disease in a classification system. We note if the patient has died after 30 days and want to analyze the relation between the Apache 2 score and the probability of death. We perform a logistic regression in SPSS, and this will be the output. The p-values are shown between sig, and here we can see that the p-value for Apache 2 score is 0.001. This means that the relation between Apache 2 score and death is significant. The first column shows the parameter estimate beta. But as we said earlier, this is difficult to interpret, so we instead consider the exponential of beta. And this is associated with a unit rise in the covariate value. So in this case, the odds ratio for death associated with the unit rise is 1.22. This means that for each unit increase in Apache 2 score, the odds for death within 30 days is increased with 22%. In logistic regression, we can't estimate R-square like we did in linear regression, but we can estimate something that is called pseudo R-square. In this case, it will be 0.104. In logistic regression, this is mostly used for comparing different models to each other. Using the result from the analysis, we can further compute the probability for death for an individual with a certain Apache 2 score. For example, we want to see the probability for death if a patient has Apache 2 score 20. Before, we could see the formula for computing the probability, and this formula looked like this. And we can impute the alpha and beta values in this formula, and we get them from the table below. The alpha is minus 4.35 and the beta value is 0.20. And if we impute those values in the formula, we will have the probability 0.42. This means that a patient with the Apache 2 score 20 has the probability 0.4 to die within 30 days. This picture shows the graph of different Apache 2 scores and the probabilities computed for each of those. You can see that for low Apache 2 scores, the probability for death is low, and for high Apache 2 scores, the probability for death is high. If we look at the Apache 2 score 20, we see that the probability for death is 0.42, and this was what we calculated before. So now we look at another example where we have one categorical variable, one categorical independent variable. We want to estimate the relation between death within 30 days and origin in the same sample of patients. Caucasian origin is here coded with 0 and African origin is coded with 1. The result looks like this. The p-value is 0.012, which means that origin is significant. The odds ratio here is 1.7, and the interpretation of this is that the odds for an African individual for death is 1.7 times the odds for a Caucasian individual. Thus, the African individual has 70% higher odds of death. As in linear regression, we can also have several independent variables. The multiple logistic regression models is written like in this picture. We continue with the same example, but now we have 3 different covariates. The covariates are Apache 2 score, origin, but we also have the variable treatment, which is coded with 0 for placebo and 1 for ibuprofen. The results look like this. When all the 3 independent variables are included, only Apache 2 score is significant. Looking at the odds ratios, we can see that 1 unit rise in Apache 2 score gives a 12% higher odds of death for that individual. Odds ratio for origin is 1.37, although non-significant. If we still interpret the odds ratio, it tells us that African individuals has 37% higher odds of death. The odds ratio for treatment is below 1. This means that the treatment group is less likely to die than the placebo group, although non-significant. So, now you have seen some example. This was the presentation about logistic regression. Thank you for listening and see you all.